Hi there and welcome to another tutorial for the Edexcel Core 3 Maths A-Level syllabus. In this video I'm going through the past paper questions that have come up on differentiation. It's my second video in this, and in particular in this video I'm focusing on turning points, when differentiation questions have come up involving turning points or stationary points. Right, as always, I'll show you the question, pause the video, have a go. I go through in 5 seconds. Right, let's do this. Part A. This curve has this equation. It asks you to find dy by dx. It's even kind enough to tell you to use the product rule. That is one function. That is your other function. So you start off by letting u be x squared and v be e to the x. So therefore u dashed is 2x and v dashed is still e to the x. And remember what the product rule says. It would say that dy by dx, in the case where you've got a u times v, is uv dashed plus vu dashed. Right, let's substitute in. Dy by dx is therefore equal to u v dashed plus v u dashed. Okay, probably best if we tidied this up. There's a e to the x here and an e to the x here, and there's an x squared here, but in particular 1x here and 1x here. So what I can do is I can factorise out an x, factorise an e to the x. I'm left with an x from this term, and I'm left with a 2 from this term. And there I have my dy by dx, and I'm done. Part B. Hence find the coordinates of the turning points. You know at a turning point dy by dx is equal to 0. The gradient function at that point is equal to 0. So the gradient is x e to the x, x plus 2. So therefore x e to the x, x plus 2 is equal to 0. Now, just to break that down, that means there are 3 things times into 0. An x times an e to the x times an x plus 2. 3 numbers times into 0, either one or all of the numbers are 0. Now e to the x can never be 0. E to the x is always bigger than 0. Remember the e to the x graph looks something like this? It can never equal 0, so that can't be 0. So either x or x plus 2 must be 0. And if x is 0, there's one answer, or x is equal to -2, that's the other answer. Now there are x values. It's asked us for coordinates, so we need to substitute x is 0 back into the original equation, which is y equals x squared x squared e to the x. And we sub back in 0, we sub back in -2, and then we get our y coordinates. When we sub back in 0, we simply get y is 0. When we sub back in -2, we get 4e to the -2. Our coordinates therefore are 0, 0, and -2, 4e to the -2. And we're done. Part C. Find d2y by dx squared. That's the second derivative. So we know that dy by dx was equal to, I'm going to keep the e to the x at the front, e to the x, x plus 2. Okay, so x plus 2. Now, this is a product as well. Here's our first function, e to the x. Here's our second function, x plus 2, which actually is probably easier if we expand out. It's easier to deal with then. E to the x, x squared plus 2x. So this is our u, and that's our v, and we're going to use the product rule again that says dy by dx is uv dash plus vu dash. We know our u, we've laid out our u as e to the x. Our u dash is therefore e to the x. Our v is x squared plus 2x, and our v dash is 2x plus 2. Okay, now substitution. dy by dx is therefore uv dash, so e to the x, 2x plus 2, plus vu dash, so x squared plus 2x e to the x. And we're pretty much done. We could just factorise out the e to the x. There's one here, and there's one here. So therefore, we leave that as 2x plus 2 plus x squared plus 2x. And when we collect like terms, we would get x squared plus 4x plus 2, and we're done. That was dy by dx. So therefore, this was d2y by dx squared. d2y by dx squared is equal to e to the x, x squared plus 4x plus 2, and we're done. Part D, determine the nature of each of the stationary points. Remember, stationary point was at 0, 0, and the other one was at negative 2 for e to the minus 2. Negative 2 for e to the negative 2. Remember how to do this. You work out the sign of the second derivative. If d2y by dx squared is bigger than 0, you have a minimum. And if d2y by dx squared is less than 0, you have a maximum. So d2y by dx squared, when x is equal to 0 for this first one here, okay, what does that turn out to be equal to? Well, it turns out to be equal to e to the 0, and then it would be multiplied by 2, which just gives me the answer 2. Therefore, it's a minimum because it's a positive number. And d2y by dx squared, when x is equal to negative 2, that would be e to the negative 2, 4 subtract 8 plus 2, and that's certainly a negative number, so it's a max. Okay, so 0, 0, state your answer, is therefore a min, and negative 2 for e to the negative 2 is therefore a maximum, and we're done. Okay, next question. June 2010, pause the video, have a go. Okay, that diagram there, I'm going to just show you there, that diagram there is a sketch of the curve C, and it's got this equation, y is 2x squared minus 5x plus 2, all in brackets, multiplied by e to the negative x. Find the coordinates of the point where C crosses the y-axis. This is the coordinate you're looking for here, where it crosses the y-axis. And that's where x is equal to 0. So for part A, for an absolutely easy mark, you let x be 0, and then y would be equal to 2 times 0 squared minus 5 times 0 plus 2, so we'd have a 2 there, e to the negative 0, and that would be 2. The coordinate of this point is therefore 0, 2, and you're done. Do state it as a coordinate. It did not ask for the y value, it asked for the coordinates, so state them. Okay, part C. Show that the curve C crosses the x-axis at x is 2, and find the coordinate of the other point where it crosses the axis. So, one of these points is going to be 2. We're looking to show that one of these points is 2, and that's when y is equal to 0. So we're going to let y equal 0, and that is to say that 0 is equal to 2x squared minus 5x plus 2, so 2x squared subtract 5x plus 2, e to the negative x. Now e to the negative x is always bigger than 0, because remember what that graph looks like. It looks something like this. It never equals 0, so you can divide both sides by 0 and get that 0 equals 2x squared negative 5x plus 2. Now how does this factorise? Well, it must factorise as 2x and x, and it must be negative 2 and negative 1. Therefore x is equal to a half, or x is equal to 2. We knew that x is 2 is one of the solutions. The other one is therefore x is equal to a half. Underline that to show you've got the right answer. Part C. Find dy by dx. Well, what was y again? Y was equal to 2x squared subtract 5x plus 2, 2x squared subtract 5x plus 2, e to the negative x. This is a function u times another function v. So what we've got is we've got u is equal to 2x squared subtract 5x plus 2. We've got u dash, therefore, is 4x subtract 5. We have our v is e to the negative x, and therefore our v dash is negative e to the negative x. The product rule says that dy by dx is equal to uv dash plus vu dash, and substituting that in, dy by dx is therefore equal to u times v dash. So I'm going to bring that negative out the front, negative e to the minus x, 2x squared minus 5x plus 2. Okay, and then plus vu dash, so plus e to the negative x, 4x subtract 5. And probably to just tidy up, I would divide out or factorise out e to the negative x. So negative e to the minus x I'll take out. I would have 2x squared minus 5x plus 2. And then dividing by negative, these would become negative, so I'd get negative 4x plus 5. And just tidying that up lastly, e to the negative x, 2x squared, subtract 9x plus 7. And I'm done. That is dy by dx. Okay, in part D, hence find the exact coordinates of the turning points. At a turning point, dy by dx is equal to 0, and we have our dy by dx, it's equal to this here, which I'll copy over. Our dy by dx is this here, and we're solving this being equal to 0. Now, as before, e to the negative x is always bigger than 0, because the e to the x graph looks something like this. So we can divide by e to the negative x and just state that 0 is 2x squared subtract 9x plus 7. We can try and factorise this as 2x x. Subtract 2, subtract 7, and we, not quite, that doesn't quite work. How else could we do it? We could, subtract 1, subtract 7, and therefore I get x is equal to 1, or x is equal to 7 over 2. It asks for the coordinates. So you need to substitute x is 1 and x is 7 over 2 back into the original equation, which was this here, which I'll just copy and paste over here. So we want to sub in x is equal to 1. When we sub in x is equal to 1, we would get y is equal to, this would be 2, subtract 2 plus 2 is 4, subtract 5 is negative. We would get negative e to the minus 1. And if we subbed in 7 over 2, what would we get? We would get 9 e to the negative 7 over 2. So the coordinates are 1 e to the negative 1 and 7 over 2, 9 e to the negative 7 over 2, and we're done. Okay, so next question. Pause the video, have a go. Right, it asks us to use calculus to find the turning points. Well, we know at a turning point that dy by dx is equal to 0. So we're going to have to calculate that. Notice we've got a quotient. We've got a function of x on the top of a fraction divided by a function of x on the bottom of a fraction. That's our u, that's our v. So lay out your u and your v. U is x, and v is 4 plus x squared. U dash is therefore 1, and v dash is therefore 2x. We know by the quotient rule that dy by dx is equal to vu dash, subtract uv dash, all over v squared. So subbing that in, dy by dx must be equal to v times u dash, which would be 4 plus x squared times 1. Subtract u times v dash, which would be x multiplied by 2x, all divided by 4 plus x squared, all squared. And if we work this out, this would be 4 plus x squared, subtract 2x squared. So it would be 4 subtract x squared over 4 plus x squared, all squared. Now, we know dy by dx is equal to 0 at a turning point. So what we want to do, we want to solve 4 subtract x squared over 4 plus x squared squared equals 0. Times both sides by 4 plus x squared all squared. We would then therefore get 4 minus x squared is 0. We would get 4 is equal to x squared, adding x squared to both sides, and that would give us x is 2 or x is negative 2. Now, it's asked us the coordinates, so we sub back into the original to get the y. When x is 2, we sub that back in, we get 2 over 8, which is a quarter. There's one value. And if x is negative 2, then we get negative 2 on the bottom over 8, so we get negative a quarter. So negative 2, negative a quarter. And we're done. For the next part, we're told what the second derivative is. We're not asked to work it out, we're told, and we're asked to determine the nature of the stationary points. Remember, the stationary points were at 2 and a quarter, and negative 2, negative a quarter. And we should know that if d2y by dx squared is bigger than 0, you've got a minimum. And if d2y by dx squared, the second derivative, is less than 0, you've got a maximum. All we need to sub in is sub in our x's, check if it's positive or negative, and we're done. So d2y over dx squared, if x is equal to 2, sub 2 into this, and you would get 4 multiplied by negative 8, which is negative 32, over, it would be 8 cubed. So negative 32 over 8 cubed, and I think you get the answer negative a 16th, therefore maximum. And the other one, d2y by dx squared, when x is negative 2, on the other hand, you would get yourself positive a 16th, and therefore you would have a minimum. And we have determined the nature of the stationary points. Okay, next question. Right, let's work through this. Use calculus to find the turning point, i.e. where dy by dx is 0. You've got a u divided by a v. It's a product rule. Our u is x, our v is 9 plus x squared, therefore our u dashed is 1, and our v dashed is 2x, and we're using the quotient rule that says dy by dx is vu dash minus uv dash all over v squared. So, what is dy by dx actually equal to? Substituting in our u, v, u dashed and v dashed. Well, vu dashed would simply be 9 plus x squared multiplied by 1. Subtract uv dashed, which would be x multiplied by 2x. And it would be all over v squared, which would be 9 plus x squared, all squared. Tidy up the top. This would be 9 plus x squared, subtract 2x squared, so we would have 9 subtract x squared over 9 plus x squared, all squared. And there is our dy by dx. And next part, we're using this result here to determine the nature of the stationary points. Hold on, just 1 second, we haven't calculated the stationary points. To do that, we're solving when this is 0. Multiply both sides by 9 plus x squared all squared. We get 9 minus x squared is 0. So you would get 9 is equal to x squared, adding x squared to both sides. So x is 3 or x is negative 3. If x is equal to 3, what's y? Sub it back in here, 3 over 18, which would be a 6th. If x was equal to negative 3, you would get y is negative 3 over 18, which is negative 6. Next part, you're giving a new function and you're asked to find the value of dy by dx at x is a half ln 3. So you're finding dy by dx. Notice dy by dx can be found by the chain rule. So y is 1 plus e to the 2x all to the 3 over 2. dy by dx, you can bring down the 3 over 2. You can differentiate the bracket. If you differentiate this bracket, you get 2e to the 2x. And then you have what you had in the bracket, 1 plus e to the 2x, but this time reduced by a 1, so you would have it to the half. Just tidying it up, 3 over 2 times 2 is 3, so you'd have 3e to the 2x, and you would have 1 plus e to the 2x, all to the power of half. Now, you want to find the value of this at x is a half, so this is dy by dx at any x. So now what you want to do is you want to work out dy by dx, but you want to substitute in x is equal to a half ln 3. And what would you get? Well, you would get 3e to the 2 times a half ln 3, 1 plus e to the 2 half ln 3, all to the half. Now, 2 times a half ln 3 is just ln 3, so that's 3e to the ln 3, 1 plus, for the same reasons, e to the ln 3 to the half. That's 3. Well, e to the ln 3 is 3, and you'd have in here 1 plus 3 to the half. 3 times 3 is 9, 1 plus 3 is 4, 4 to the half is 2, so this would give you the answer 18, and you're done. Next question. Pause the video, have a go. Okay, going through this, by writing sec x as 1 over cos x, show that the derivative of sec x is sec x tan x. Well, this is easy. You just say that sec x is 1 over cos x, which is cos x all to the power of minus 1. So if y is equal to this, dy by dx is bring down the negative 1, differentiate the bracket, and you would get negative sine x, and then reduce the bracket in powers by 1. The negative here times the negative here would cancel, and you would have sine x. Cos x to the minus 2 is 1 over cos squared, which is like a cos x times cos x on bottom. Now, you can think of sine x over cos x as being tan x, and you can think of a hidden 1 here, and you can think of 1 over cos x is equal to sec x, and you've got your answer, sec x tan x, as you required. So dy by dx is sec x tan x. B, you're given that y is equal to e to the 2x sec 3x, find dy by dx. You should spot one function multiplied by another function. It's of the form u times v. Our u is e to the 2x, our v is sec 3x, our u dashed is therefore 2e to the 2x, and our v dashed, well, going to the previous part, we know that the derivative of sec x is sec x tan x. So if you differentiate sec 3x, you differentiate the bracket, you get 3, and then you know it's sec 3x tan 3x. The derivative of this. Okay, let's do some substitution. dy by dx is given by the product rule as uv dash plus vu dash. Subbing in, it would be e to the 2x, 3 sec 3x tan 3x, plus vu dash, which would be sec 3x multiplied by 2 e to the 2x. You could factorise out the e to the 2x, and you could also factorise out a sec 3x. You would be left with a 3 here and a tan 3x, and you would be left, sec 3x would be gone, the 2 would still be there, and you'd be left with plus 2 as follows. So that's your dy by dx. Okay, and next part, the curve of this equation between negative pi by 6 and pi by 6 has a turning point at AB. Find the values of the constant AB. to three significant figures. Well, we know what dy by dx is. We're told that dy by dx was equal to e to the 2x sec 3x, e to the 2x sec 3x, and then we would get 3 tan 3x plus 2. Now for a turning point, that's equal to 0. Now, you know that e to the 2x can never equal 0, so you can divide both sides of the equation by this, and you would just get the following, would equal 0. So either 3x equals 0, or 3 tan 3x plus 2 is equal to 0. If sec x is equal to 0, sec x can never equal 0, so you can ignore this. Remember the sec graph, if the cos graph looks something like this, remember the sec graph then looks something like this, and it never has the values 0. So the only answers we're going to get is where tan of 3x is equal to negative 2/3. So 3x is the inverse tan of 2/3, which if you type in your negative 2/3 even, so if you do that, you do the inverse tan of negative 2/3, keeping your calculator of course in radians mode, you get a negative 0.588 for 3x. Now you draw your tan graph. Now the range was between minus pi by 6 and pi by 6, but you're looking for 3x, so you times that by 3, and really the range is between pi by 2 then and negative pi by 2. So negative 0.588 is here at just 1 point, so x is therefore this negative 0.588 divided by 3, which is negative 0.196, and you're done. Okay, next question. Right, let's go through the answers. There's your curve. You want to show the turning points are at tan x is negative 1. Okay, you have got a u multiplied by a v, a u times v. Your u is given by e to the 2x. Your v is tan x. Your u dash, the differential, must be 2e to the 2x. Your differential of v, the differential of tan x, you should know, is sec squared x. Okay, now you differentiate using the formula for the product rule, which you should always write down. uv dash plus vu dash. Let's sub in. dy by dx is therefore u e to the 2x times v dash, which is sec squared x, plus vu dash, so tan x, and then times 2e to the 2x. You could factorise out an e to the 2x here, and you'd be left with sec squared x here plus 2 tan x, and you would get that as equal your dy by dx. Now, for a turning point, you must have dy by dx is equal to 0. E to the 2x can never equal 0, so really what you're solving is sec squared x plus 2 tan x is equal to 0. Now, you can't solve this currently. There's secs going on here, and there are tans going on here. Could you make them all in terms of sec or tan? Well, you know one of the rules, you know that 1 plus tan squared x is sec squared x. Okay, that is one of the identities you need to be able to use. So instead of having sec squared x plus put 1 plus tan squared x plus 2 tan x is 0, replace it there, and this is a quadratic. Tan squared x plus 2 tan x plus 1 is equal 0, and then you can factorise that as tan x plus 1 all squared is 0, so tan x as required is negative 1, and you're done. And part B, find the equation of the tangent to C at the point where x is 0. So you want to work out dy by dx when x is equal to 0 for the gradient, and that would be, you know that the gradient is equal to this here. So dy by dx is, it would be e to the 0, subbing in 0 into this up here, it would be sec squared 0 plus 2 tan 0. So sec squared 0 plus 2 tan of 0. Now, I know that tan of 0 is 0, and I know e to 0 is 1. I also know that sec 0, which is 1 over cos, sec squared 0, which is 1 over cos squared 0, is 1. So that has value 1. So the gradient is 1. When x is 0, what's the y coordinate? Well, going back to the original equation, would be e to 0 tan 0, which again would be 0. So you can use the formula y minus y1 is mx minus x1. So y subtract 0 would be equal to 1, x subtract 0. So the tangent would be equal to y is equal to x. Okay, next, here's the question. Pause, have a go. Okay, part A says find f dash x. So we're differentiating this here. So let's go ahead and give it a go. We differentiate this. This differentiates to 3e to the x. This differentiates to, you subtract half ln. Ln differentiates to 1 over x. And 2 differentiates to 0. So f dash x, just tidying up, would be 3e to the x, subtract 1 over 2x. Show that alpha is equal to a 6th e to the minus alpha, and what is alpha all about? The curve of f of x has turning point at p, the x coordinate of p is alpha. So for a turning point, you know dy by dx is equal to 0, and on the previous page we had dy by dx, or f dash, is 3e to the x minus, subtract 1 over 2x. So 3e to the x subtract 1 over 2x is equal to 0. Add 1. Now, careful to read the question here. It tells you that the x coordinate of this turning point is alpha. So if I put alpha into this equation, that solves this equation. And it's asking us to show that alpha is this. To rearrange this in this form, well, I could add the 1 over 2x to both sides. So 3e to the alpha is 1 over 2 alpha. I could flip both sides, so I could have 1 over 3e to the alpha is equal to 2 alpha. And then I could divide by 2. I could say alpha is therefore 1 over 6e to the alpha. Therefore alpha is a 6th e to the minus alpha, or negative alpha, as required. Part C then says you've got the following iteration. The next one in the sequence is a 6th e to the one previously in the sequence, where x0 is 1. It says is used to find an approximate value for alpha. Calculate the values of x1, x2, x3, x4. x1 would therefore be equal to 1/6 e to the negative x0, which is 1. You type that in your calculator. To the negative and you get yourself 0.0611313. You're supposed to give it to 4 decimal places, so 1, 2, 3, 4, that's sufficient. Then the next one, x2, would be a 6th e to this number here. You can use the ANS function in your calculator. So you do that and you would get 0.1568. You do it another time using the ANS function in your calculator, you would get 0.1425. And you do it one more time on your calculator and you would get 0.144. 4, 5. And there are your x1, x2, x3, x4 to 4 dp. And part D, it says, by considering a suitable change of sign for f-s in a suitable interval, prove that alpha is equal to that to 4 dp. If you think alpha is 0.1433, you need to check a little bit to the right hand side of it, 0.14335. You need to check a little bit to the left of it, 0.143, so that should be 325. And what you do is you work out f dashed of 0.14325, and you're going to work out f dashed of 0.14335. So you're going to sub it back into f dashed, and f dashed is this here. Okay, so you are going to put that in your calculator and work it out. So it would be 3 negative 0.0007 it would be, and the other one would be 14335. You get 0.02, and you can say change of sign plus continuous, therefore root between 0.14325 and 0.14335. So the root is 0.1433 to 4 dp. That's accurate. And last question, there it is. Pause, have a go. Okay, it tells us here's a curve, and we want to, the curve has a minimum point at P. The x-coordinate of P is K, show that K satisfies that equation. Well, for a minimum, you work out dy by dx. So you've got a u multiplied by a v. So what we do is we use the product rule. Our u is 2x subtract 1, so our u dash would be 2x. Our v is tan 2x, so our v dash is 2 sec squared 2x. And we use dy by dx is equal to uv dash plus vu dash. And therefore we say that dy by dx is equal to 2x subtract 1 v dash, which would be 2 sec squared 2x, plus vu dash, which is tan 2x times 2. And you could factorise out, well, there's no point, we'll just leave it as that for now. And at a minimum, dy by dx is equal to 0. So therefore this thing is equal to 0. So we could say that 2x subtract 1 multiplied by 2 sec squared 2x plus 2 tan 2x is equal to 0. We want to show the equation is satisfied by this here. So at we've got sines in here, and we haven't got sec squares or tan, so probably my only option here is, actually the one thing I could do first is to divide everything by 2. So I have 2x subtract 1 sec squared 2x plus tan 2x is 0. Because none of these give me a sign, the best thing to do is convert this into its meaning, which is 1 over cos squared 2x plus sine 2x over cos 2x is 0. Want to add fractions, I need to multiply this one by cos 2x on top and bottom, so I'd get plus sine 2x cos 2x all over cos squared 2x. Could now multiply everything by cos squared 2x to get rid of that on the bottom, so I would have 2x subtract 1 plus sine 2x cos 2x is equal to 0. Now you should know that one of your identities is that sine of 2a is 2 sine a cos a, so therefore this here must be equal, if I've got here on this side simply a sine 2x cos 2x, then that must be equal to a half sine 4x. Okay, so this whole thing here must be equal to a half sine 4x. A half sine 4x is 0 plus the 2x subtract 1 times everything by 2, and I get 4x subtract 2 plus sine 4x is 0. And k was the point that this happened, so I can just sub in k at the end and I get what I'm asked to by the examiner. And I'm done. Part B, calculate x1, x2, x3 and x4 to 4dp using this iteration. Well, x1 is going to be a quarter to subtract sine 4 of 0.3. So tap that in your calculator, you type in a quarter to subtract sine of 4 aunts, and you get for x1 0.266 to 4dp 9 it would be, but that would round everything up, so therefore this would be, once rounded up, 0.270. The next two, just doing it again, would be 0.2809, and one more time x3 would be 0.2746, and one more time x4 would be 0.2774. Finally, to finish then, show that this is a root to 3 significant figures. Well, if I want to show this is a root, I've got to check to the right of it 0.2775, and I've got to check to the left of it 0.2765, and I need to put that into the original equation from which the iteration came, namely this one here. Okay, 4k plus sine 4k subtract 2 is 0, so my f of x or f of k is 4x plus sine 4x plus sine 4x minus 2. 4x subtract sine 4x minus 2 is a plus, sorry, is a plus, and I work out f of 0.2765, I work out f of 0.2775 and hope for a change in sign. Let's see if I get that. Be 4x plus sine 4x subtract 2. You want to calculate it where x is equal to 0.2765, and I get myself a negative answer here. I get negative 0.00009, and if I try a different answer, 0.2775, I get 0.006. So change in sign, continuous, therefore root between interval, and therefore this shows k is 0.277 to 3 significant figures. And I'm done. So I hope you found the following video useful in your revision for differentiation, and in particular calculating turning points. Thank you for watching.